Okay. Hello, everybody. I'm really excited to be here. Thank you for coming to my talk, Shatter Reloaded, where I'll talk about how we revived Shatter attacks in order to escape sandboxes and evade endpoint security products. So a little bit about myself. My name is Eran. I am the engineering lead for Accenture Security Israel as part of the R&D team. So now let's dive right into the matter at hand. So a bit about the history of Shatter attacks, how it all started. So it all started in one rainy day in 2002, where this guy, Chris Paget, published an article titled Exploiting Design Flaws in the Win32 API for Privilege Escalation, or Shatter Attacks, How to Break Windows. So in this paper, he describes this attack that he has, where he uses a WM timer Windows message sent to a target process, and that message has a pointer to a callback that will be executed. Now, this callback, he injects some code using an edit box control, and then the pointer to the callback points to that code. The target process would usually be some Win32 service running as system and showing some GUI to the users. The way this attack would work is, first of all, the attacker would find the edit box in the target process and call send message to it, sending it to WM set text message. This set text message would receive a buffer, which would be copied over to the target process. This buffer would obviously contain the shellcode. Now, the second step, he would find this shellcode inside the target process. So he could do that in one of two ways, either by scanning the memory of the target process or just running it in a lab environment using a debugger and assuming that the address will be the same always, which was true at the time. Once he has the address of that shellcode, he would then send a second message to the target process, this time a WM timer, containing a pointer to that address that he found, thus achieving code execution. Now, Microsoft saw this, and they said, OK, how can we stop this? So eventually, what they did is they patched the WM timer so that it won't be able to execute any timer that wasn't previously registered with the set timer API. Also, they started a move to stop those services from showing GUI to the users, because that's a bad practice. But that's not good enough, because WM timer is just one example of a Windows message that can do that, because there are other Windows messages that also receive a pointer to a callback and then just execute it. So rich edit controls has a few. List view has one for sorting items, and a tree view also has one for sorting its children. So let's take a step backward and see why were these attacks even possible in the first place. So the first reason is that there were no access control mechanisms for Windows messages between processes in the same desktop. So any process, even one running as guest, could send a Windows message to any other process in the same desktop, even one running as system. The second thing is that there were services running inside the user's desktop. So the same desktop has both user processes and services running as system. The third thing is that some services running as system expose a GUI to the user. And that's bad, because if they expose a GUI, that means they can be interacted with by normal users. And fourth, remote Windows messages could contain pointers to a shellcode that will then be executed by the target process. So the combination of all these together allows us to achieve this Shatter attack. Then came Windows Vista. And Windows Vista put in a few security fixes to prevent these things from happening. So the first thing they did, they introduced a mechanism called User Interface Privileged Isolation, or UIPI. This held something called mandatory integrity control, or in other words, each process will receive an integrity level, low, medium, high, or system. Normal processes would usually get medium level, elevated processes would get high, and system processes would get system. And this mechanism would prevent Windows messages from being sent from one process to another if the target process has a higher integrity level. Another thing they did is they introduced Windows Session 0 isolation. So if until now a first user connecting into the computer, logging in, would log into Session 0, this is no longer the case. Now a new user would receive Session 1, 2, and so on, and Session 0 is reserved only for these system services. Also, they introduced the interactive service detection, which is a mechanism that said if there is a service that tries to show GUI to the user, then it will open up this ugly message box, this ugly pop-up, and say to the user, there's a service trying to show you some user interface on another desktop. Do you want to go over to that desktop and see it? And this kind of forced all vendors, Microsoft and third-party vendors, to stop showing GUI in their services. So this basically put a stop to Shatter attacks being able to escalate the privileges. So then they were soon forgotten, never to be used again. That's until we came along. So we looked at some modern use cases and saw how we can use Shatter attacks in them. So our first use case is a commercial sandbox that we got to check. Now, how this sandbox worked, it divided all the processes in the computer into two separate groups: trusted processes and untrusted processes. Trusted processes are basically all your corporate apps. So every app that has access to your corporate data, and those apps would not have access to the internet or external-facing networks. Then you have the untrusted processes, which are everything else. Basically, all the apps that come from unknown sources, or all the ones that communicate with the internet. And these would not have access to your corporate data. Now, the isolation would be implemented over multiple domains. So file system and registry, for example, all untrusted processes would receive a different view of the file system and of the registry, so they wouldn't be able to see all the files that are naturally there on the computer. So if you have a folder with some files, an untrusted process might see that folder open or not even existing at all. And also write operations would be isolated. Also, on network isolation, as we said, trusted processes could not access the network. The isolation was also on process boundaries, so opening another process for writing was no longer possible. It was possible for reading. Sandbox did not stop opening another process for reading, and more about that later, but we couldn't open it for writing. So the usual use case of, let's say, virtual alloc-ex to allocate some executable memory in the target process and write process memory to inject our shellcode into it did no longer work. Also, sending messages, Windows messages from an untrusted process to a trusted process. That was also blocked by the sandbox. Reading a clipboard from an untrusted process written by a trusted process. Printing the screen, such as with BitBLT, all those were blocked by the sandbox. So we looked at it a little bit more, and we said, OK, what can we do with it? How can we still exploit it? So we looked at the file system and registry, and we saw that those were pretty well implemented. They used mini-filters in the kernel, so we couldn't bypass that. Then we went on, and we looked at the process boundaries. So can we open another process and write to it? And that was also implemented pretty well. They used a mechanism called object callbacks, or the function OB register callbacks. And what that function lets you is, it lets you define a callback that will be called whenever, according to configuration, one of the following happens. Either you create, open, or duplicate a handle to a process thread or desktop. So they could set a callback that will be called whenever someone tries to open a handle to an existing process. And if that request is with write access, then they would deny it. So again, we couldn't bypass that. So how can we still escape that sandbox? So then we looked at sending Windows messages. And what we saw is that this sandbox implemented this isolation using user mode hooks. Now, the problem with user mode hooks is that they are found in user mode. That is, entirely inside the user mode memory space. And thus, since they are in our process's memory space, our process can remove those hooks. It can unhook itself. And that's exactly what we did. We unhooked ourselves from these user mode hooks, and lo and behold, we could now send a Windows message to a trusted process. Does this scenario ring a bell? Can't see how that could be useful. So, bringing back Shatter attacks from the dead, we researched a little bit, and we found this tripolin attack. And this attack, what it did is it used a different window message from the original Shatter attack. It used TVM sort children CB, which is a message sent to tree views. And they would inject their code using virtual alloc-ex and write process memory to get their code into the target process, and then use this window message to the tree view in order to pass a pointer to that callback and execute it. So this is nice, but we need a different method to inject our code because we cannot open another process for writing. So let's assume for a second, and we'll soon see why we need this assumption and what can we do with it. Let's assume we have a trusted process in the machine. And it has an edit box, a status bar, a tree view, and some readable, writable, and executable memory. Sounds far-fetched, I know, but wait for it. So to inject our shellcode, first of all, we look for the edit box, and we send it a Windows message of WM set text to send it our shellcode. Now, a small improvement that we did is that instead of calling the normal send message A function, we call the Unicode version of it, and then we can pass any shellcode that even has null bytes, just not double nulls. So that was a small improvement. Then the next stage, we would find our shellcode inside that target process. Now, since the sandbox did not block opening another process for reading, we can open it for reading, go over all its allocated memory, and find our shellcode. Now, back in the day, in 2002, DEP, or data execution prevention, did not exist yet. But today it does. So once we injected our shellcode into this edit box buffer, that's no longer enough because that memory is not executable. So we have to somehow transfer it into some RWX memory. So what we do is, first of all, we find this RWX memory that we assume that we have. Then we use the status bar that, again, we assume that this process has in order to do the following. We send it two Windows messages. The first is a set text message. And the set text message, to differentiate from the edit box's set text message assumes that the pointer it gets points to a memory range in the source process. For a status bar, that is not the case. The pointer points to an address in the target process. So set text to the status bar means copy something from somewhere inside the target process's memory range into the status bar's buffer. So we send it the pointer of the shellcode, of our shellcode that we found earlier. And then we send it another message, this time getText, and gave it a pointer to the RWX memory that we found, to some code cave that we selected in there. And that would copy the shellcode from the status bar's buffer and into the RWX memory. Once we have that, we have our shellcode inside RWX memory, and all that is left is to send a tree view a message of tvm sort children CB, give it a pointer to our shellcode, and our shellcode executes. Now, apparently, a new Windows 7 x64 has all of the above. The Windows Explorer, explorer.exe, it has right there on the top right, it has an edit box where we can search for files. On the left, we have a tree view where we can see a nice tree of all the files on our system. On the bottom, we have a status bar. It's actually not the one you see there. The real one is hidden, and we can't see it. But it's there, and that's all that's important. We don't need to see it in order to interact with it. And this explorer.exe had one single page of RWX memory right there off the box. So no changes needed. It already has all these things. So we can then move on with our attack. Basically, given a shellcode that doesn't have any double nulls, what we did is, first of all, we find the addresses, the handles, to all those UI elements that we need, so the edit box, the tree view, and the status bar. We find the RWX memory region inside the process, and we select our code cave inside it. In this case, we chose the end of that region. Then number 3, we create a buffer that will serve for the window message, for the tvm sort children CB message, because it needs to receive some struct with the data. And number 4, we created a buffer that holds our shellcode and that buffer from number 3 together so we can inject it. Number 5, we send the edit box a WM set text message with this buffer to inject it to the target process. We scan the memory of explorer.exe, and we find our shellcode inside it. Then, in number 8, we send a message to the status bar of set text and give it the address of our shellcode, and getText from that to copy that shellcode into the RWX memory that we found in step number 2. Finally, we send the tree view a tvm sort children CB message, giving it the pointer to our shellcode inside the RWX memory. And again, we achieve code execution. Now, this worked fine for proof of concept, but when we came to weaponize it, we encountered two small problems. Now, the first one, the first pitfall, is that the compare functions could be potentially called many, many times. Why is that? Because if you have a tree view and it has a lot of children, then all those children need to be compared to each other to see what the sorting of the tree will be. So what we did to solve this is we added this assembly line, this move byte ptr REP-7 0xC3. We prepended our shellcode with that, and what that line does is basically it overwrites the first byte of the shellcode, or rather the first byte of this line, to be a ret opcode. And what this does is that every subsequent call to this shellcode will just execute ret and return back to the caller. So then our shellcode would run only once. Now, the second thing we saw is that sometimes the Explorer, the File Explorer window is not open. Now, if the window is not open, then we have no status bar, no edit box, and no tree view to interact with. So we have to open one of our own. What we did is we called shell execute, giving it a parameter of open and a valid path such as /, and gave it a parameter, a flag of SW hide. This flag tells the system to open the window in a hidden mode, so the user will not see anything. We then inject our shellcode as before, and we can even close the window because now our code is running from the memory space of that process. So that was the first use case that we saw for this Shatter attack, this sandbox. And the second use case is that we wanted to inject code and whilst evading EDRs. So modern EDRs, or endpoint security mechanisms, they are very sensitive, and they really don't like it that you try to inject code from one process to another. And if, for example, you try the classic method of code injection using open process to open the remote process for writing, then virtual alloc-ex to allocate some writable memory inside it, a writable executable, sorry, write process memory to write your shellcode into that process, and create remote thread to run that shellcode that you injected, any self-respecting EDR today would block you from doing that thing. So, Shatter attack to the rescue. However, this test was not done on Windows 7, it was done on Windows 10. And apparently in Windows 10, it is no longer true that Explorer.exe has some RWX memory inside it. So we said, OK, we need RWX memory in order to execute our code from. So what can we do with that? So what we can do is we can send TVM sort children CB messages. And what those do is they receive a pointer, and they call this compare function according to the pointer that we give them. So let's look at the signature of this callback function. So this callback function, right on the bottom, it receives three parameters: lparam1, lparam2, and lparam sort. The third parameter it receives from the struct that we provide to the TVM sort message, sort children CB message. So if you see on the top, we have this struct, this TV sort CB struct, and its second field is the pointer to the compare function. The third field is the lparam that will be passed as a third parameter to all calls of this compare function. Now, the first two parameters, lparam1 and lparam2, are received from the tree view items. So if we want to compare two items, we need to get some data from each one of them in order for some comparing logic to occur. So basically, each element in the tree, each child there, has an lparam value. And those lparams are passed to this function. So what we can do is we can remotely enumerate the children of this tree view, and we can call setItem for each of them, thus setting the value of the lparam. So that way, we can control all the values that are passed to this function. Only small problem is we don't know the order in which Windows will decide to call to compare the elements. So maybe if we have two elements, maybe this will be the one called for lparam1 and this for lparam2, and maybe this one will be for lparam1 and this one for lparam2. But we'll soon see why we don't care really about the order between the first two elements. So bottom line is we can call any three-argument function that we want. So we need some RWX memory. So in order to generate some, to allocate some readable, writable, and executable memory, we looked at virtual alloc, which is the obvious choice for this. Only problem is that virtual alloc gets 4 parameters, not 3. And the fourth parameter is the one of the protection flags, the one in which we need to specify that we want this to be an RWX memory. So we must control this parameter, and since we can't, then this function is not good for us. Also, the other versions of this function, whether it be virtual alloc EX, virtual alloc EX NUMA, virtual alloc from app, virtual alloc 2, virtual alloc 2 from app, and even the lower level NTDLLs, NT-allocate virtual memory, all of those receive at least 4 parameters, and we need to control at least one parameter, which is fourth or higher. So then we said, OK, if we can't allocate some new RWX memory, maybe we can change some existing memory to be readable, writable, and executable. So that's what virtual protect is for. However, virtual protect also receives 4 parameters. Now, it seems on first sight that the interesting parameters are the first 3, because you got the address of the memory that you want to change, the size of it, and the new protection flags. And the fourth parameter is simply a pointer to a DWORD that will receive the old protection flags that were true for this memory range. Now, we thought, OK, maybe we can just wing it somehow pass null to it, and thus telling the function that we don't care about the old protection flags. But Microsoft were pretty clear in their documentation, and they said that if this parameter is null or does not point to a valid variable, the function fails. So we must control this fourth parameter as well, and we can't use virtual protect either. Also, the other versions of virtual protect are also not good for us, virtual protect EX and virtual protect from app, and NTDLL's anti-protect virtual memory. All of those receive at least 4 parameters, and in all of them, we need to control at least one parameter, fourth or higher. So we thought about this some more. We scratched our heads. We Googled a bit. We looked around. And finally, we found this function, heap create. Now, what heap create does is it creates a new heap. Other than you have the default heap for each process, heap create creates a new one. And heap create is perfect for us. And why is it perfect? Well, first of all, it receives only 3 parameters. And that's great, because we can call a 3-parameter function. Now, the first parameter is the options flag. And apparently, heap create supports a flag that is heap create enable execute, which makes all the memory inside the created heap executable, in addition to already being readable and writable. The second parameter is the initial size of the heap, and the third parameter is the maximum size. And luckily for us, heap create creates all this memory already committed and ready to use. It's not just reserved or something. So basically, what we did is, first of all, we enumerated the children of the tree view, and we set item for each of them, setting their lparam values to this heap create enable execute flag, which is 0x40,000. Because we don't know if it will be passed as a first or as a second parameter to our function. Now, since we don't know the order and we set all of them to this value, this means that also the second parameter of heap create will be called with this value. Now, 0x40,000 is 256 kilobytes. So that's also fine, because it's probably not as large to make an allocation fail, but it's large enough to contain any shellcode known to mankind, and obviously also good enough for us. And third parameter, as we said, we can fully control it, so we can just pass 0, for example, which tells heap create to create a heap that can grow as much as we need. So then once we have these, we can basically create our own RWX memory, and Shatter attack can work as it did in Windows 7, right? Well, almost. We had one more challenge to fix. Apparently, the status bar filters some bad characters, some unprintable characters. So any character, any white character of the form something, null byte, where something is between 1 and 0x1f, except for 9, which is tab, all of those would be converted to 0x20 and a null byte, which is a space. Now, this is OK if we only need to transfer our shellcode, because shellcodes can be encoded to only have printable characters, or alphanumeric characters, or not have null bytes, or not have bad characters. But we also need to transfer our set item structs, our TV item structs, which are needed for the set item calls. And those structs have sequences of null bytes, and they have all these bad characters in them, and they can't be encoded. They need to be transferred as is. So how can we solve that? What we did is some special handling for those wide characters. So let's say that we had a source buffer that is the one here, AABB0500 and CC, and we want to transfer that structure, that buffer, to the target process. So we looked at the first wide character, and we see that it's AABB, which is not a filtered character. So we can just transfer it in the normal way. We can send the edit box a set text message, then set text for the status bar from the edit box, and get text from the status bar into a target address. Now we looked at the second wide character, and we see it's 0500. Now this is a filtered character, so we can't just copy it as is. So what we do is we go 1 byte backwards. And once we do that, we see that we have BB05. That's a wide character that we can copy. So then we copy that over, but not to offset 2, but to offset 1 of our buffer. So then the BB overwrites the previous BB. That's fine, we don't care. And 05 is also appended to that buffer. We go on, and then we see that we have 00 and CC. That's not a filtered character, so we can just copy it as before through the edit box and the status bar. That way, copying 1 wide character at a time and going back 1 byte if needed, we can copy any buffer that we want, even one with multiple null bytes in a row and with bad characters. So once we did that, we managed to copy all our TV items structs for set items. We can set all the items L-params and call heap create to get some readable, writable, and executable memory. And then we could continue as before and achieve code execution once again. So we want to check this on those EDRs. So we took one leading EDR in the market, and we said, OK, let's see how our code behaves with it. So first of all, we tried some good old create remote thread to load library injection to see that the EDR indeed works and does what it's supposed to do. So as expected, we did that, and all the alarm bells went off, and the EDR said, OK, I saw that this process is trying to inject some memory into explorer.exe and run it with create remote thread, and that's bad, and I'm stopping you from doing that. So that was blocked. And then we said, OK, now let's try our code. And when we tried our code, there were no alerts. So what the EDR did find is it found that we did open process on ourselves and anti-protect virtual memory and find first file exw, which are all part of the Py2exe's loader setting up the embedded Python interpreter. Then he saw that we did create window exw, which is probably caused by the shell execute that we ran in order to create our window. Anti-query system information to find the PID, the process ID of explorer.exe. And finally, open process for explorer.exe, but a read-only open. And the EDR did not consider that as malicious. He let us do it, and that was the last thing he saw us do. Everything else went completely under the radar. So once again, code execution, win. So to recap, what we did is we took an 18-year-old security-related design issue in the Win32 GUI. We brought it back from the dead to see how it could be used in modern operating systems and in modern use cases. And what we saw is that basically the root cause for this to be able to happen is that there is all this complex and dangerous behavior with pointers inside Windows messages. So sometimes a pointer is considered to be pointing to data in the source process, like in the case of the edit box's set text. And that data should be copied from the source process to the target process. Sometimes these pointers were pointers to data inside the local process, like the status bar's setText and getText. Those meant that data should be copied inside the target process's memory range. And sometimes these pointers point to a callback to some code that should be executed by the target process. Combining these together, we had enabled the allocate RWX memory, write to arbitrary address, and execute arbitrary address primitives. And with those, we could inject and execute any code. So some possible mitigation ideas. Well, one thing we could do is we can hook send message and prevent or block all kinds of dangerous Win32 messages. So for example, things like set text and get text for a status bar coming from a different process, or the TVM sort children CB coming from a different process, or any of the list of messages that contain a callback. They should not be coming from a different process. So if we hook this and prevent those from happening, then that could be better. However, as we said, user mode hooks are not good enough because they can just be unhooked. So a different thing we can do is use a mechanism from Windows called Windows hooks, which is called by calling the set window hook ex function. And we can call it with either the call winproc or the get message arguments. What those would do is they would inject DLL into all the processes inside this desktop and specify a callback that would be called whenever either the Windows procedure is going to be called or a message is received in a process. And that callback could verify the safety or the security of this message coming along. And it could block any dangerous messages. So luckily for us, Windows has this mechanism. It just needs to be used. So a few closing thoughts. First of all, we should not rely on user mode hooks because they are not good enough. Since Windows introduced patch guard, we can no longer hook in the kernel. We can't put kernel hooks, so all that is left is just user mode hooks. But that's not good enough. That's a gap that exists here because any user mode hook can be unhooked or detoured in some way. So Microsoft really needs to come in here and put in some new mechanism to allow security products to secure us by hooking the correct functions, but not in user mode. In addition, I believe Windows can really benefit from something like Linux's LSM, or the Linux security modules, which is something that allows to implement things like AppArmor or SE Linux above it. Those will allow to define some per process, per API policies, and they can mitigate or stop certain kinds of attacks, certain kinds of dangerous operations from happening. So before we part, to finish up, let's watch a little demo. Second. OK. So there we have a Windows 10 machine. And I'm going to run our code, which what's it going to do is basically it's going to do all the steps that we saw before. So it's going to call shell execute in order to open a new hidden Windows Explorer window. Now, because it's hidden, we won't see anything on the screen. It will then find all the controls, all the UI elements that it needs inside it. So the edit box, the status bar, and the tree view. It will then enumerate all the tree view children. And for each of them, it will copy a buffer over to the other side and call set item with that buffer, thus setting the lparam value to 0x40,000. Once that is done, it will send the tree view a message of tvm sort children CB. That will, with a pointer to the heap create function. That will call heap create with the correct parameters and allocate us some readable, writable, and executable memory inside the process. Then it will inject our shellcode with all the, how we saw it with the edit box and the status bar. It will inject our shellcode into the target process. And finally, it will send another message of tvm sort children CB with a pointer to our shellcode that will run our shellcode. What our shellcode does is simply just pop up a message box, which we will see that it opens up from Explorer. So I will run this code. 1 second. Yep, there we go. And a message box pops up. If we look at the source process, sorry, 1 second. Wait, I lost it. Oh, there it is. If we look at this process, we can see that it comes from explorer.exe. And we can also bring to front and see that it is. And 1 second. Wait, that's not good. And we can see the icon here on the bottom, which is Explorer's icon. So there we have it, code execution from Explorer. So I thank you all for coming to my talk. And we have some more time for questions if anyone got it. Thank you.
How big of an effort was it from the idea to the success with Windows 10?
Sorry?
Much time?
How much time? So the sandbox was about 1 month of research, and EDRs was maybe another few weeks. Any more questions? OK, thank you very much.